Hi, my name is Brian Magnuson, and today I'd like to introduce an algorithm called driver prediction that is used to improve fuel efficiency of a hybrid vehicle powertrain. So for the past 2 years, my research group and I at the University of Washington have been designing and building the powertrain that this algorithm is intended for. It is a series plug-in hybrid electric vehicle. And basically, it's been donated to us by General Motors, and the powertrain is being installed into a 2016 Chevrolet Camaro. So to improve upon the already efficient powertrain control of this series plug-in, driver prediction attempts to learn the route the driver intends to take, as well as the speed the driver will take over the predicted route. And what this allows the algorithm to know is changes in elevation and changes in vehicle acceleration ahead of time so that it can forecast points along the route where basically energy can be captured using regenerative braking. So knowing these spots where energy can be captured can then be used to minimize the amount of gas energy used in the powertrain ahead of time. So this little model kind of shows how driver prediction is augmented into a normal driving scenario. First, the algorithm receives GPS and vehicle speed data while the driver drives. While the driver makes decisions of where to go and how fast to go during their drive, driver prediction basically tries to learn these habits and predict them using information from the previous step. And then information is relayed to what's called the vehicle optimizer, and this is the predictions from the driver prediction as well as the pedal requests from the driver. And basically, the vehicle optimization attempts to minimize the amount of gas energy used from the powertrain by knowing points along the route ahead of time where it can be regained or recaptured. Next, information is relayed to the vehicle to be controlled accordingly, and kind of the process repeats itself. So driver prediction is a two-part model in order to learn and predict driver behavior. And the first step is route prediction, which employs a hidden Markov model. And basically what it does is predicts the end destination and then the route that the user is likely to take to get to that end destination. So it first starts by locating the vehicle on a map and then predicts the next series of intersections that the vehicle is most probably going to take in order to get to that end destination. And then basically as the vehicle drives along the route, it checks to ensure that the predicted route is actually what is being driven. And if it is wrong, then it'll update its prediction at the intersection where the driver may have deviated from the prediction. So the importance of route prediction is basically I'll go back 2 slides, sorry. To understand changes in elevation. That's the big takeaway ahead of time, before the driver actually drives down that portion of the road where there might be a hill, for instance. The next part of the model is speed prediction. This employs a neural network and predicts the speed trace along the predicted path from the route prediction part. This video here basically showcases how fast the model can change to sharp adjustments in vehicle speed over time by basically mimicking the activation of neurons like a human brain. The key aspect of speed prediction for this algorithm is to basically know in advance what the acceleration of the vehicle and how it's going to change over time. So hopefully by now it's a little bit clear how driver prediction can forecast spots along the road where energy can be recaptured using regenerative braking. Doing software-in-the-loop testing with a virtual world and a virtual car, results showed about a 5% increase in fuel energy efficiency of our series hybrid. So if you apply these improvements to a commercial vehicle, you can show the impacts of it. And a study here is generated by the U.S. Department of Energy over the customer fleet of Chevrolet Volts as of 2014. And in this study, it said that basically the Volt is capable of achieving 35.3 miles per gallon while using its onboard generator, and 38% of the time the generator is used during normal driving conditions. So if you assume that your average driver drives 15,000 miles per year, then in 2014 the Volt fleet would have consumed about 9.39 million gallons of gas. And though it's a small increase, the 5% increase in fuel efficiency that driver prediction offers could, in theory, save 470,000 million gallons for that fleet in that year alone. So that's my presentation. Thank you.